How do nuclear weapons work? At the center of every atom is a nucleus. Breaking that nucleus apart, or combining two nuclei together, can release large amounts of energy. Nuclear weapons use that energy to create an explosion. Chemical explosives, nuclear fission, and nuclear fusion are all used in the operation of modern nuclear weapons. The nuclear material is compressed by the explosives, which causes fission. The fission then releases enormous amounts of energy in the form of X-rays, which raises the temperature and pressure to the levels required for fusion to begin. Fission and fusion. All matter is composed of atoms, incredibly small structures that house different combinations of three particles, known as protons, neutrons, and electrons. Each atom has a nucleus at its core, pluralized as nuclei, which is where neutrons and protons are tightly connected to one another. The majority of nuclei are reasonably stable, which means that the distribution of their neutrons and protons is largely constant and unchanging. The nuclei of some heavy atoms split apart into smaller, lighter nuclei during fission, releasing extra energy in the process. This may occasionally happen on its own, but in some nuclei, it may also be induced from outside. Instability and fission are brought on by a neutron being fired at the nucleus and being absorbed. In some elements, such as specific isotopes of uranium and plutonium, the fission process also releases surplus neutrons. If these neutrons are absorbed by neighboring atoms, they can start a chain reaction. In modern nuclear weapons, which use both fission and fusion, a single warhead can release more explosive energy in a fraction of a second than all of the weapons used during World War II combined, including Fat Man and Little Boy, the two atom bombs dropped on Japan. Fusion works in reverse. When exposed to extremely high temperatures and pressures, some lightweight nuclei can fuse together to form heavier nuclei, releasing energy in the process. All nuclear weapons produce an explosion through fission. Little Boy, the first nuclear weapon ever deployed in combat, functioned by firing a hollow cylinder of uranium-235 into a target plug made of the same substance. Only particular isotopes of specific elements can fission. An isotope is a variation of the same element with different numbers of neutrons in the nucleus. The most frequent isotopes are uranium-235 and plutonium-239. Only particular isotopes of specific elements can fission. An isotope is a variation of the same element with different numbers of neutrons in the nucleus. The most frequent isotopes are uranium-235 and plutonium-239. Each piece by itself was not enough to constitute a critical mass, the minimum amount of nuclear material needed to maintain fission, but by colliding the pieces, critical mass was reached and a fission chain reaction occurred. Modern nuclear weapons work slightly differently. Critical mass depends on the density of the material. As the density increases, the critical mass decreases. Instead of colliding two subcritical pieces of nuclear fuel, modern weapons detonate chemical explosives around a subcritical sphere, or pit, of uranium-235 ore. Modern nuclear weapons work slightly differently. Critical mass depends on the density of the material. As the density increases, the critical mass decreases. Instead of colliding two subcritical pieces of nuclear fuel, modern weapons detonate chemical explosives around a subcritical sphere, or pit, of uranium-235 ore. Plutonium-239 metal. The force from the blast is directed inward, compressing the pit and bringing its atoms closer together. Once dense enough to reach the critical mass, neutrons are injected, initiating a fission chain reaction and producing an atomic explosion. In fusion weapons, also called thermonuclear or hydrogen weapons, the energy from an initial fission explosion is used to fuse hydrogen isotopes together. The energy released by the weapon creates a fireball that reaches several tens of million degrees, temperatures in the same range as the center of the sun, which also runs on fusion. The explosions used in thermonuclear weapons are often described as a primary, the chemical and fission explosions, and secondary, the subsequent fusion blast. However, the actual mechanisms are considerably more complicated. Modern nuclear weapons work slightly differently. Critical mass depends on the density of the material. As the density increases, the critical mass decreases. Instead of colliding two subcritical pieces of nuclear fuel, modern weapons detonate chemical explosives around a subcritical sphere, or pit, of uranium-235 ore. For example, a pure fission primary is inefficient. The plutonium pit will blow itself apart before most of the plutonium-239 can fission. Instead, the reaction can be boosted by including hydrogen gas, consisting of the isotopes deuterium and tritium, in the center of a hollow pit. As the surrounding plutonium fissions, the hydrogen gas undergoes fusion and releases neutrons, inducing additional fission. Similarly, the secondary doesn't consist purely of fusion fuel. Layered within it is a fission spark plug, consisting of either plutonium-239 or uranium-235. As the primary explosion compresses the fuel from the outside, the spark plug material becomes supercritical and fissions, heating the hydrogen from the inside and facilitating further fusion reactions. Only a small number of elements are utilized in nuclear weapons, despite the fact that many of them are fissionable, able to undergo fission. The most prevalent isotopes are plutonium-239 and uranium-235. Reminder: isotopes are atoms of the same element that differ only in their number of neutrons. Only a small number of elements are utilized in nuclear weapons, despite the fact that many of them are fissionable, able to undergo fission. The most prevalent isotopes are plutonium-239 and uranium-235. Reminder: isotopes are atoms of the same element that differ only in their number of neutrons. Plutonium can also be used, but only occurs naturally in trace amounts. It can, however, be produced as a fission byproduct in nuclear reactors, then separated by a process called reprocessing. Plutonium separation is easier than uranium enrichment. It involves separating different elements, not different isotopes of the same element, but it's a highly radioactive process that requires heavily shielded facilities with remote handling equipment. The United States was the first country to develop nuclear weapons, detonating the first fission device in 1945. 7 years later, the United States successfully tested the first hydrogen bomb during Operation Ivy. Physicist Richard Garwin helped build that device, and today serves on the board of the Union of Concerned Scientists. As of 2018, the United States had an estimated 6,500 nuclear warheads, including retired, awaiting dismantlement, stored, and deployed weapons. The Earth is home to uranium, which may be mined from mineral sources. It can also be extracted from seawater, but doing so is currently much more expensive. However, uranium-235 only makes up a tiny portion, less than 1%, of naturally occurring uranium. The process of enrichment, which involves separating and concentrating various uranium isotopes, is necessary to produce usable uranium, usually using centrifuges, which operate like salad spinners. This is one of the most expensive, challenging, and time-consuming things that. Aside from France, 300 warheads, other nuclear-armed nations include China, 260, the United Kingdom, 215, Pakistan, 130, and India, 120. Israel hasn't formally admitted to having nuclear weapons. Its arsenal has traditionally been estimated to contain 80 warheads, while other estimates are far higher. At the peak of the Cold War in the mid-1980s, the world had a combined total of over 60,000 nuclear warheads. Today that number is closer to 15,000, representing a 75% reduction. This progress was made possible thanks to leaders and advocates who recognize the very real dangers of nuclear war. Even a limited nuclear exchange could kill millions of people, cause severe climate effects, and wreak havoc on the world's political and economic structures. A full-blown nuclear war would do irreparable harm to the world as we know it. More work remains to be done, including further cuts, faster dismantlement, and alerting. Hundreds of U.S. missiles